Hi team, welcome to my science lab, also known as my kitchen. And the reason I'm using this as a science lab is because I'm going to use it to help demonstrate some visualizations of some of the scientific concepts or physics concepts that are so important to understanding how our homes work. Now the first concept I'm going to cover is that of condensation. Now condensation is where water, which is in water vapor, so gas form, cools down and becomes liquid. Now for me, the best place to see this in action is by looking up to the sky, because this is the fundamental principle of how clouds form. And the further away you move from the Earth's surface in elevation, so as you gain altitude, the air cools. For the geeks amongst you, it cools at roughly around 2 degrees per 1,000 feet. And if it cools enough, the tiny water vapor molecules turn to liquid and it forms the clouds. The clouds are the liquid that you can see being formed from the water vapor molecules. Now I appreciate this is a difficult concept to grasp because clouds look like they're floating, it looks like they're a gas, and yet you can see them. And what I'm saying is you can't see the water vapor. So I'm now going to use one of my kids' toys just to help illustrate this point. So you've got to use your imagination, and each of these tiny little magnetic stony things are a molecule of water, so one H2O molecule. In this water vapor phase, they are individual molecules and they are teeny tiny, infinitesimally small that you simply cannot see them when they're surrounded by the air around them. And because each of these molecules are a gas, they have quite a lot of energy, so they're bouncing around and moving all the time. And each time they collide with each other, they lose a little bit of that energy. And what happens when they lose their energy is that it's affected them cooling down. They actually then bind together because they don't have sufficient energy to keep bouncing off each other all the time. So as the water vapor is cooling, actually what's happening is all these tiny little molecules are bouncing into each other and clumping together. And they form microscopic droplets. And these droplets are actually what scatter the light, and that's what looks like cloud or fog forming. But because the droplets are tiny, the upward movement of air and normal air turbulence can still keep them suspended. They only fall when they grow large enough. Now when this all happens, from it being a vapor turning into a liquid, is down to the temperature. The critical temperature point at which it turns from being water vapor into liquid water and forming the cloud, that temperature is known as the dew point temperature. Now I love this particular video because it shows exactly where the dew point temperature is on this image as the clouds are forming. So as we can see, the wind is blowing from right to left. Now the air mass that is being pushed and drafted up that slope, up the side of that mountainside, is a moist air mass. As it's being pushed up, it is cooling, as I mentioned, roughly around 2 degrees per 1,000 feet of cooling. When it gets to around the peak, it's reaching its dew point temperature. So it's turning from being a water vapor into a liquid, which is where you can see it as the cloud forming. Love that video. And here's another one we can see. Water vapor in our breath cooling rapidly to dew point as we exhale into a cold air. Right, so let's get off the topic of meteorology because that's not why you're here, and let's now start applying it to our buildings. Now to understand where we're at with that point of condensation, in other words, where the risk is of the humidity inside our buildings getting to the point of condensing on a surface, be it glass or a wall or otherwise, we need to understand a few key concepts, and I mentioned them previously just now. One is the actual humidity of the air, which here on this hygrometer is being shown as the relative humidity, more on that later, and the other is the temperature. You need both of those to understand and determine what your risk is of moisture in this air condensing. One figure alone, the relative humidity, doesn't do that. You cannot rely on this figure to understand whether or not you are at risk of things condensing in the room. That is, unless it's already at 100%. But if this was at 100%, you would see fog in the room. The whole point is that means that the moisture is already at the point of condensing, so you'd actually see all those particles in the air, which would be fog. Let's go more into that. The point with this relative humidity is understanding the percentage of moisture that the air can possibly hold at that given temperature. For example here, this means at 20 degrees, roughly 20 degrees, which it is in this room, the air is holding 51%, so just over half the amount of moisture that it is able to hold. And what I mean by able to hold is that if you keep on adding more water vapor into this air, you can only get up to 100%, and then you start to see it. Then it turns from being a gas into a liquid. That's the fog. So this air at the moment is currently filling 52%. So the relationship between these two, the temperature and the relative humidity, is crucially important. As you probably know, having high humidity in a room, in a house, is not particularly healthy, and it can lead to mold growth and condensation and things. But often one of the solutions to reducing the humidity in your home is to ventilate, so is to open the window and get that moist air out. Some of the arguments I've seen online, and some people have contacted me about a bit of confusion on this, is that, well, surely it's wetter outside because it's raining and it feels colder, therefore aren't I going to be letting more moisture in? I'm going to explain why that often isn't the case, and actually the outside air, certainly in the winter, is almost always drier than the inside air. Let's unpack that a bit. Now, I took this video a little bit earlier, and as we can see, I measured the temperature here in the kitchen at 19.5 degrees C and 46% relative humidity. I then had a hygrometer outside, which I'd left out there for a little while, to acclimatise the outside temperatures. And you can see the outside air temperature is then 5.6 degrees at 64% relative humidity. Now, on the face of it, it looks like it's wetter outside. It looks like 64% is the humidity outside versus 45% or 46% inside. But that's not the full story. I'll explain more. So I'm going to use those two bits of data we've got to show a visualization of the difference in the amount of actual water we've got in the volume of air inside versus outside. And to understand that, I'm going to be calculating the absolute humidity. Now, there's different terms in terms of introducing here. So, but the absolute humidity is measured in the number of grams of water per meter cubed. So I'm going to use these set of scales, which measures in grams, and I'm going to take a representative sample of 10 meters cubed of air. So imagine outside or inside a 10 meter cubic space. So cubic space of air is about the size of a large room, is going to be represented by this glass. So imagine this is 10 meters of cubed volume of air, and I'm going to measure how many grams of water are in that. There's 10 cubic meters of inside air, and then there's 10 cubic meters of outside air. Let's pop those on the scales. Let's start off with the outside air. We'll just zero that to make sure it's reading the same. So this is now our outside air. So let's now add our number of grams of water vapor in the outside air. This is measuring the absolute humidity. 10 cubic meters of outside air, 45 grams of water. That is the same as 4.5 grams per 1 cubic meter. That's what we've got. Now let's do the same for the inside air. 10 cubic meters of inside air. Now we're going to add how much water is in our 10 cubic meters of inside air. 77 grams. So 77 grams per 10 cubic meters, which is the same as 7.7 grams per cubic meter. Let's look at the difference between the two. Okay, so I kind of hear what you're saying here, which is that's a lovely experiment, Rich, and you've just shown us that there's more grams in this cup than there is in this cup. Why, therefore, do we not always calculate or measure, should I say, the absolute humidity of a space rather than the relative humidity and the temperature? Well, the simple reason is just having a figure of number of grams per meter cubed isn't particularly useful to understand what risk you're taking when it comes to condensation. You need the other factor as well. For example, if a particular room was at 15 degrees and it had 8 grams per cubic meter in it, that wouldn't necessarily give me any information in terms of whether or not that air in that room was at high or low risk of condensing on those surfaces. You need to have the relative humidity and the temperature both together to then calculate what we call as the dew point. I hope I've demonstrated here that almost always in the UK, when the weather is cold outside, even if it's potentially foggy, the outside air is almost always drier than the inside air. Now, what that means is if you have a humidity challenge or you're getting lots of condensation in your home, then opening the window is a good way to replace the wet inside air with the drier, cold outside air. Now, I understand what many people have said to me on this when I've mentioned it before, in terms of, yes, but then surely you're losing all your heat out in that warm, moist air going outside. And you'll be right. Now, I haven't yet finished devising the experiment yet, because one of the things I want to get across is understanding just how quickly opening the window and exchanging that air mass and getting the cold, dry air in really makes a difference to the humidity and reducing the humidity in a room, and how little heat loss you get. And let me just explain why that's the case. We heat our buildings generally using radiators that heat up the air. That air is extremely efficient at transferring its heat into the fabric, into the walls, into the surfaces and the furniture around us. When we open those windows and we exchange the air mass and we reduce the humidity inside and then close the windows again, yes, we've now got an air which is colder and drier, but what then happens is the heat that was dissipated already and radiated into those surfaces, like your furniture and your walls, radiates back out again into heating up that cold air. And in a relatively short period of time, the room is back up to the temperature it was, or negligibly slightly less, because it's taken some of that heat energy out of the walls and surfaces around you. So I do acknowledge opening a window first thing in the morning when you're not even dressed yet is a shock to the system, is a shock to feeling that cold air coming in. But the benefits of opening the window for a few minutes, getting rid of that moisture, closing the window again, means you've then got dry air in your room, which is warmed back again quite rapidly through all the heated surfaces of the walls and furniture. And then you've got the benefit of the dry air not running the risk of condensing on the colder surfaces. As I say, I'm going to try and do some calculations and some experiments to put that into real empirical value in terms of opening a window for a period of time, how much the temperature of the room drops down, how much it costs to then reheat that room from the radiated from things, versus, for example, running a dehumidifier for a couple of hours to get the same benefit of reduction in humidity. I'm pretty confident that opening a window for 10 minutes is going to outperform the cost of running a dehumidifier, probably by a factor of 5 at least. So I hope that little kitchen experiment with our inside air and outside air and weighing them has helped to really demystify what these devices are really useful at being able to show us, but also understand that outside air in the winter is drier than inside air, and opening your windows can have a fantastic effect on reducing your risk of condensation and mold growth in your homes versus running a dehumidifier. If you've enjoyed this video, give us a like. If you think other people might benefit or this would be helpful to others, send it to them. Follow along if you want to see more in videos like this, because I've got another one coming up specifically about dew point, where I'm going to talk a bit more detail about some of the risks involved with identifying where those areas in your house are at greatest risk of condensation and therefore mold growth. Cheers.